have a look at page 2 of your worksheet. Page 2 of your worksheet. Okay, right. So we start with the first question there. Under page 2 of your worksheet, they tell you in a double slit experiment, the distance between the fringes on the screen was too small to measure. Okay, this one, when you hear mention of double slit experiment, this one is already two source interference. Okay, so this one normally refers to the double slit experiment for light, Young's double slit experiment. Okay, so this one is actually talking about the two source interference cases that we've discussed. They tell you the distance between the fringes on the screen was too small to measure. All right, in the double slit experiment, the distance between the fringes on the screen was too small to measure. So you shine light onto a double slit like the ones that is seen on page 12. Shine light on the double slit. And then on the screen, you see a pattern of, you see an interference pattern. Okay, so right now, what they're talking about is that the distance between the fringes that is observed on the screen is too small to measure. Okay, it is too small to measure. So what would increase the distance between the fringes? Okay, so here I know the this is double slit. I know this one would have to use, this one will be referring to two source interference. When they say distance between fringes, this one will be referring to X. Okay, with double slit is two source interference pattern, this equation would always apply. Lambda is equals to AX over D. Okay, so they tell you the distance between the fringes that is observed on the screen is too small to measure, meaning to say X is too small, right? What will increase the distance between the fringes? In other words, they're asking you how to increase X. So since you know this is a double slit, it's two source interference pattern, you're going to always use this equation. Okay, so lambda is equals to AX over D. Make X the subject. X is lambda over D divided by A. So right now from here you can see that if X increase, then lambda increase, D increase, or A decrease. Either one of these changes must occur in order for X to increase. Either lambda increase, D increase, or A decrease. All right. So let's look at the answer choices one by one. Okay. Now, if you look at answer choices A, increasing the distance between the light source and the slits. Distance between light source and slits, this one, you need to be careful. Distance between light source and slit, this is not D. Okay. A lot of times people mistake this as D. Okay, if you look back at page 12 of your notes, capital D is referring to the distance between the slits and the screen. Between slit and screen. If I wanted to draw a simple representation of the diagram here, this is what you have. Okay, so this one is here. This one is your bright and dark fringes. This one is your X. This one is your X. This one here is your A. This one here is your capital D. Distance between slit and the screen. Okay, so this one is your double slit. This one is your screen. Okay, distance between light source and slits is actually talking about this. This one, if say is your light source, the distance between light source and slit is actually this unknown quantity here. Okay. Okay. So distance between light source and slit is referring to this. Okay. It's not referring to the distance between slit and screen. So okay, this is not D. All right. So slit separation is only affected by lambda, D, and A. So since this is not talking about D, this one cannot be the answer. All right. This one actually has no effect. All right. Actually, it's not to say no effect. You have no effect on fringe separation, but right fringe is less bright. Okay. No effect on the fringe separation, but the bright fringe will be less bright. Because what will happen is that if you try to move the light source backwards so that the distance D is increased, what will tell you is that light has to travel further, the intensity has decreased or is less bright by the time it reaches the slits. Okay, so if you try to increase the separation between your light source and slits, your light actually has to travel a much further distance. Before it had to travel only this much, but now it has to travel a much further distance. It will actually become less bright by the time it reaches your double slit. So the interference pattern that you form will actually be less bright. But fringe separation itself, no change. Okay, because it did not affect any of these parameters. Okay, but here we're not talking about the brightness of the fringes. We're just interested in the fringe separation. So A is not the answer. If you look at increasing the distance between the slits and screen, this one is increasing D. All right. So this one should be the answer. But let's check with the other answer choices. How about C and D? Now, increasing distance between slits, what does this do? Increasing distance between the slits is actually increasing A. It is not what we want. We want A to decrease. So C is out. And now after that, you look at the last choice, increasing frequency of the light source. Okay, while it does not relate directly to the wavelength, you have to make the connection there. You remember that frequency is inversely proportional to wavelength. So if frequency increase, wavelength should drop. Okay, so right now we want wavelength to increase, but this one is telling us wavelength is dropping. So D is out. The only correct answer is therefore B. Okay, right? Okay, so this one is all right. Okay, then if you move on to the next question, June 15 P12, I'll just clear out the drawing here. What is not an essential condition? Notice that they actually bolded some of the words there. What is not an essential condition for an observable interference pattern to occur between waves from two sources? Waves from two sources, interference between waves from two sources, this is two-source interference. Okay. Now they want to know what is the essential condition for observable interference pattern, meaning to say you can see the pattern. Now, observable interference pattern, you can think of observable as implying steady. Okay. it can be read as, but it's not an essential condition for steady interference pattern to occur between waves from two sources. So as I mentioned to you, steady here would mean the interference pattern does not change location with time. The places where you see constructive and destructive interference don't change places with time. They are fixed, no matter how long you leave it there. Okay, so one of the conditions just now I mentioned was that the waves must be coherent. So here they tell you sources must be coherent. This one I know must be essential. Now, also I mentioned to you, coherent already implies frequencies of the sources must be equal, right? So these two are actually the same. Answer choice A and B are actually talking about the same thing. All right. Sources must be coherent, that one I explained. If they tell you frequencies of the two sources must be equal, this one already implies coherence, therefore is essential. All right. And then after that, if you look at answer choice D, the wave from two sources must overlap. This one is also supposed to be essential. This is also essential because for interference to occur, the waves must overlap or meet in the first place. Okay, interference pattern is formed by interference of the waves. For interference to occur in the first place, they must meet. All right, so this is also essential. The one that is not essential is actually this. Okay, all right. The source must emit waves of equal amplitude. Okay, equal amplitude ensures good contrast between constructive and destructive. Okay, so but it's not the most essential. Is not essential. Okay, the pattern can still be seen even if the pattern can still be seen even if amplitudes are not equal. Okay, so A, C, D, sorry, A, B, and D are essential. It's only C that is not essential. Okay, if you want to see an interference pattern, first thing first, coherent. Second thing, they must overlap. Amplitude not being equal, that one is actually not the most essential. Amplitude being equal ensures good contrast. All right, it's good to have, but it's not the most important. Okay, even if the amplitudes were not equal, you can actually still see the pattern, just that it isn't as clear. All right, so 26 is C. All right, okay, so that one is okay. Then after that, if you just look at page 3 of your notes, sorry, not the notes, page 3 of your worksheet. Okay, over here we tell you a pattern of waves was observed without being able to view the source of the waves. Okay, the pattern is represented in this diagram. Okay, so you see here they tell you region of maximum intensity is represented by these lines here. Okay, it's basically represented by the, okay, no, maybe I don't draw these lines like that. Regions of maximum intensity is represented by this. Okay. I mean, you can draw it properly using a ruler later on. Okay, regions of maximum intensity is the pink colored line. Okay, region of minimum intensity is the region in between the maximum intensity. In other words, is the region between the constructive interference. That one will be represented by this. Okay. All right. It's actually this pattern here for the water waves. It's actually very similar to this pattern that you see in your notes under page 6. Okay. This one is the interference pattern, right? You have alternating constructive and destructive interference. Constructive will give you maximum intensity. Destructive will give you minimum intensity. All right. So what caused this pattern? You know that this pattern is actually caused by two source interference, right? So the pattern is represented in the diagram. You can say that the pattern is caused by interference of waves. Okay, this one, that much you know. All right. Now there's also another thing here. All right. There's another trick to this question. For the waves to interfere, they had to spread out from the source. Therefore, diffraction is involved too. Okay. For this answer, the answer of this question, they want you to explain the phenomenon that caused this interference pattern to be seen. Okay. Now you do know that when you have the regions of constructive or destructive or regions of maximum or minimum intensity is due to the waves meeting or interfering with each other, so you have interference. That is correct. You had two choices here, interference only or diffraction and interference. There's another thing you needed to know here. You have to go one step further. You have to know that in order for the waves to meet and interfere, they had to spread out from the source. So diffraction is involved here. If let's just say I say that this is light wave lah, it could be that I have a double slit here. All right. So I have wave that come to the double slit. So once the wave hit the double slit, as the wave passes through each slit acts as a wave source itself. And then from there, the waves actually spread out. The reason why they're able to spread out is because of diffraction. Okay, so it's after they're able to spread out due to diffraction that they meet, overlap, and interfere, which in turn gave you this one. Okay, so the correct answer for this one is diffraction and interference. Interference is correct, but it's not the full answer. It is diffraction and interference. All right, so answer is B. Maybe I should just write here. The pattern of maximum and minimum intensity is caused by interference of waves. Okay, for waves, the interference that spread out from the source, therefore diffraction is involved too. Okay, right. So that part is okay. Then after that, we go on to something else. Okay, now just look at the bottom page here. Sorry, it's still page 3. Okay, you're still under page 3. All right. Look at the question 28. Now, which electromagnetic wave would cause the most significant diffraction effect for atomic lattice spacing of 10 power minus 10 meter? Okay. So most significant diffraction effect, I mentioned diffraction to you guys before in one of the earlier parts of the notes. If you look at page 3 of your notes, it was mentioned that when size of opening is comparable to the wavelength, significant diffraction occurs. Now, comparable to size of opening being comparable to wavelength, you can just think of it as being similar in order of magnitude. Or in other words, the power of 10. Right? So what I mean by that is that if I tell you 2 times 10 power minus 3 versus 5 times 10 power 3, this one is same order of magnitude, but value is not the same. Okay, 2 times 10 power 3 and 5 times 10 power 3 obviously do not have the same value, but they are same order of magnitude. Okay, so if I give you 2 times 10 power minus 6, this one, if you just look at the power of 10s alone, this one is different value, obviously, and also different order of magnitude. When you want to evaluate order of magnitude, you normally look at their power of 10s. Okay, if they have the same power of 10, then that means same order of magnitude, but they do not necessarily will be the same value. Case in point is this. All right, this one is actually equivalent to 2 millimeter. This is, sorry, if this one is meter, this one would be 5 millimeter. Okay, and then this one here is 2 micrometer. Okay, so if I just talk to you about this one, you would clearly tell me it's not the same value, right? But it's actually the same order of magnitude. And then if I ask you to compare these two, you would tell me it's not the same value. It's also not even the same order of magnitude. Okay, so back to this one. For significant diffraction effect to occur, you need to have similar order of magnitude. All right, between your opening and your wavelength, between the gap and your wavelength. So right now they've already given you the size of your gap. Atomic lattice spacing of 10 power negative 10 meter. You need to find something with, you need to find a wave whose wavelength is similar order of magnitude to have significant diffraction. So this one similar in order of magnitude to have significant diffraction. So you're talking about electromagnetic wave. What will tell you is that you need to reproduce your EM wave spectrum again. So this one is something I mentioned to you. You need to remember how to reproduce the EM wave spectrum. So this one will always be 10 power 3, 10 power 0, 10 power minus 3, 10 power minus 6, 10 power minus 9, 10 power minus 12. Always leave a space for 10 power minus 7. So raging Martians invade Venus using X-ray gun. So you want to find out which wave has 10 power minus 10. Okay, the wave that seems to have 10 power minus 10 is actually going to be X-ray. 10 power minus 9 to 10 power minus 12, right? Going here is lambda decrease now. Okay, so your answer here would be X-ray. Okay, X-ray has similar order of magnitude to 10 power minus, its order of magnitude is same with the lattice spacing. Okay, 10 power minus 10. It also has 10 power minus 10. So therefore, X-ray will give you the most significant diffraction. Okay, so that one is okay. All right. Okay, so answer is D. Okay. If there's anything I needed to add, okay, now this one I'll say wavelength and gap must have similar order of magnitude. Okay, must have similar order of magnitude. If I want to write out the wordings properly, wavelength and the gap must have similar order of magnitude. In other words, same power of 10 to a significant diffraction. And then you reproduce your EMA spectrum. So X-ray has 10 power negative 10 for lambda, therefore is the answer. Okay, so 28 is D. Okay, then you move on to page 4. This one is talking about path difference for you. Now, wave generators at point X and Y produce water waves of the same wavelength. At point Z, waves from X have the same amplitude as waves from Y. Distances XZ and YZ are as shown. The wave generators operate in phase. Okay, this is a keyword. When the wave generators operate in phase, the amplitude of oscillation at Z is 0. What could be the wavelength of the waves? Okay, so what you're having now is wave generators at point X and Y. This is one wave source. This is one wave source. Both of the waves have the same wavelength and they're traveling towards point Z. Okay, so wave from X will go to Z, wave from Y will also go to Z. So eventually they'll meet at Z itself. All right. So what was mentioned here is that when the generators were operating in phase, meaning to say that sources are in phase, what was found was that at Z, the amplitude oscillation is 0. So this one tells you destructive interference occurred. All right. They mentioned to you earlier also that they have same wavelength, right? Okay. Waves from X and Y have the same wavelength. Okay. So if they meet at Z and you get a 0 amplitude, this one already tells you that destructive interference occurred. All right. So this one is important information number 1, sources in phase. This is important information number 2, destructive interference occur. So now the third important information now is path difference. You see they gave you lengths here. All right. And then they tell you what happened here. So once you do enough, you will start to relate this to the concept of path difference. So if the sources are in phase, and you know that destructive interference occur, so you know that destructive interference occur. What I mentioned to you previously was that for destructive interference, your path difference must be equals to lambda over 2, 3 lambda over 2, 5 lambda over 2, and so on. If I try to word it properly, this one will be 0.5 lambda, 1.5 lambda, 2.5 lambda, and so on. Okay. So this one is this, right? You can also say it's n plus half lambda if you wanted to. Okay, this is all the important information here. Now the question is asking you what could be the wavelength of the waves, all right? So over here, you see your path difference. Your path difference is, what's the difference in the length traveled between wave X and wave Y? It is 34 minus 24, giving you 10 centimeter. Right? So your path difference is 10 centimeter, but you want to express it in terms of fraction of a wavelength. Okay, express the path difference in fractions of wavelength. Okay, so let's just say your case here, you already have the possible values of wavelength. What you do is you express the path difference first. Path difference in fractions of lambda. Okay, so this one, the path difference in fraction of lambda would be 10 divided by 2. All these values here are actually lambda, 2 centimeter, 3 centimeter, 4 centimeter, 6 centimeter. So what you want to do is that for each of these given wavelength, you try to find out what would be the path difference in terms of those given wavelength. This one is 10 divided by 2, giving you 5 lambda. This one will be 10 divided by 3, giving you 3.3 lambda. This one is 10 divided by 4, giving you 2.5 lambda. This one is 10 divided by 6, which will in turn give you 1.7 lambda. So you know that disruptive interference path difference must be these values here. 0.5, 1.5, 2.5. It must be having 0.5. So the only one that seems to have 0.5 is this one. Okay, this one is 2.5 lambda. So the answer is C. The rest is not possible because it's telling you something else. Okay, so answer is C. Okay, so far so good with that. Okay, then after that, I move on to the next question. Page 5 I cannot do, page 6 I cannot do. Okay, the next page you can do is page 8. Okay, the next page you can do is page 8. All right, you have two overlapping waves of the same type that travel in the same direction. The variation with distance x or the displacement y of each wave is as shown. Okay, you have two different waves here. This is your displacement distance graph. They tell you the speed of the waves is 240 meters per second. The waves are coherent and produce an interference pattern. Explain the meanings of coherence and interference. So this is June 15, P23. Wait, let me open up for you. Coherence just means constant phase difference. That's all it meant. Okay, you can just write that. Let me just open up the answer for you. What question is this? Question 6. Yeah. So explain the meaning of coherence and interference. You can just say constant phase difference between the waves. Okay. That is what you would always say. Constant phase difference between the waves. All right. Now, when we ask you to explain coherence, don't say the waves have same frequency, same wavelength, same period, same speed, and whatever. Okay. The formal definition of coherence is strictly this: constant phase difference. It's because you have constant phase difference that you get same frequency, same period, same wavelength, same speed, and whatever. Okay, so just remember this. Coherence is always just constant phase difference. All right, and then the next thing they'll ask you is what is interference? Okay, you can just say overlapping of the waves and addition of the displacement of the two waves to give a resultant displacement. All right, if this one sounds a bit difficult for you to remember, you can always just use back the definition from the first page of your notes, which was this. Where two or more waves meet, resultant displacement is the sum of individual displacement of each wave at that point. It means the same thing. This is also interference. Okay. What you have here written in pencil is actually another way of talking about the same thing. Waves overlap and addition and adding the displacement of the two waves to give you a resultant displacement. Okay. Or you can just use back the definition from your notes. Where two or more waves meet, the resultant displacement is the sum of displacement of each wave. Okay, you don't really need to use the word vector sum. Okay, last time I used to use that wording, but it's not necessary. You can just omit this. You can just follow the definition that's inside your notes. All right. Okay, so that part is okay. Now, for part 2, use figure 6.1 to determine the frequency of the waves. Okay. Now, it won't matter which wave you use from the above, because the waves are actually coherent in the first place. You already know that they have the same frequency and subsequently the same period, same wavelength, and whatsoever. Okay, so it won't matter which wave you use, okay, because they are coherent. Every other parameter is the same: wavelength, period, speed, frequency. Okay, so just choose one of the waves. You can easily see that their wavelength is going to be 3.2. Okay, if let's just say I use this wave, I can clearly see that this one is 3.2 meter. This one is 3. So this is 3.1. This is 3.2. You want to use that info to find your frequency. Use P equals to F lambda. You know the speed. You know the wavelength. You can find the frequency now, which is this one. Okay. You will get the answer as 75 Hertz. Okay, so that one is okay. All right, then after that, the question will ask you, state the phase difference between the waves. What is the phase difference between these two waves? Okay, so this is where you will make use of what you learned in the previous chapter when it comes to finding phase difference between two waves. I mentioned to you before that if you want to find phase difference between two waves, you just pick 2 points that are similar to each other. Either the crest and crest, trough and trough, or the equilibrium position going down or going up. So in your case, you have the two waves, which is this one. And then you have the second wave, which is this one. Okay. So you just pick 2 similar points first. The easiest one for you to choose is going to be this one and this one, because these two are crests. So this one here to here, the difference is going to be, I think, 0.8. Now, usually when you want to find phase difference, you always need to find it in terms of fraction of a cycle, right? So to find it in terms of fraction of a cycle, you need to know how much is the value of one cycle. If I refer to the part that I highlighted in orange, this one is one cycle. Okay, maybe I should use a different color. Sorry. Okay. This one here is one cycle, which is 3.2 meter. Okay. So now you can find out your phase difference. Your phase difference is going to be 0.8 divided by 3.2, giving you 0.8 divided by 3.2 gives you the fraction of the cycle, but you need to multiply with 360 to get it in angles, in degrees, because you see the answer here is in degrees. So if I want to write out the answer properly, my phase difference is 0.8 over 3.2 of a cycle. It's 0.8 over 3.2, change to degrees. I will get 90 degrees. I will get 90 degrees. This is the answer. Okay. All right, so 90 degrees. Okay, then after that, part 4, use principle of superposition to sketch on figure 6.1 the resultant wave. Okay, use principle of superposition to sketch on figure 6.1 the resultant wave. So you had these two waves here just now, the green colored wave and the orange colored wave. Now they want you to sketch the resultant wave that is formed when these two waves meet. Okay, so just now I highlighted those waves for you. This is wave number 1. This is wave number 2. Okay, so principle of superposition tells you that at the point where waves meet, the resultant displacement is the sum of displacement of the waves. So you need to find out the resultant wave here. An easy way is to look at some convenient points. I'll just mark out the convenient points for you. You see, this one is 0, and then this one is 2. So 0 plus 2 obviously will give you 2. So your new point is going to be here. All right. And then you look at this one. These 2 points are where they meet, right? This one is actually 1.5 for the green wave, 1.5 for the orange wave. So 1.5 plus 1.5 gives you 3, which would be this point here. Okay. Then another easy point to use would be this point here. Wait, let me draw it out. You see, this one is 0, and then again this one is 2. So 0 plus 2 gives you 2. This is your other point. Okay. So you pick these 3 convenient points from the rest of the wave. You plot out the points, and then you draw out the shape. Your resultant wave shape should be like this eventually. Okay, you should look like this eventually. Okay. So just pick the convenient points and you should get the answer. Okay, so what they just want to see is that your sketch has an amplitude of 3 centimeters. That one will give you 1 mark. And then after that, they want to see correct displacement values at previous peaks to produce the correct shape. This one, just think of it as they want to see roughly a correct shape, which is the one that's highlighted in blue. Okay. All right, this one might take some time for you to do. So this one, you do it later when you have time. I move on to the last part of the question first. All right. Okay, now you have an interference pattern that's produced using the arrangement shown in figure 6.2. Okay, this one is your Young's double slit experiment. You see got double slit, got laser light. You know it's Young's double slit already. Okay, so what they tell you is that light of wavelength lambda 546 nanometer is incident on the slits S1 and S2. The slits are distance of 0.13 millimeter apart. The distance between the slits and screen is 85 centimeter. 2 points on the screen are labeled A and B. The path difference between S1A and S2A is 0. The path difference between S1B and S2B is 2.5 lambda. Maxima and minima of intensity of light are produced on the screen. Okay. So right now they ask you to calculate distance AB. Now when you read this statement here, maxima and minima of intensity, maxima refers to the bright fringe, minima refers to the dark fringe. Okay, maxima, minima intensity are produced on the screen. Meaning say bright and dark fringes are produced on the screen. They ask you to calculate distance AB. What is the distance from here to here? Okay. Now, there's one important part here that you can see. They tell you the path difference between S1A and S2A is 0. What is the significance of this statement? This tells you that this indicates that A is the central fringe on the center line. Okay, this same experimental setup, the interference pattern you get looks like what you see on the page 12. Okay, you have a double slit, you have a screen. If you shine a light through a double slit, the lights will spread out, giving you bright and dark fringes on your screen. Okay, so right now, based on what you see here, point A, because the path difference is 0, you see, this would tell you that the A is actually is the central fringe, is on the center line itself. Okay, that one is the first fact you can see. And then they tell you path difference between S1B and S2B is 2 lambda. So what's the distance between AB then? All right. Now, what you have over here is actually something like a small cutout of what you have under page 12. Okay. So remember just now I mentioned to you at the center where you have your bright fringe, your path difference is 0. And then when you have your first bright fringe, your path difference is lambda. The second bright fringe, your path difference is 2 lambda. And then this, you can also do the same analysis for your dark fringe. It will be 0.5 lambda, 1.5 lambda, 2.5 lambda, right? So of interest to you is the S1B and S2B, where they tell you it's 2.5 lambda. If your path difference is 2.5 lambda, it's going to tell you that you have a dark fringe. Okay, 2.5 lambda is a dark fringe. Okay, but what's the position of the dark fringe at 2.5 lambda? It's actually somewhere here. Okay, you have your first bright fringe, second bright fringe, third bright fringe. Immediately after the third bright fringe is a dark fringe. That one will be at a path difference of 2.5 lambda. Okay, so that is what you're supposed to see from here. This one tells you your bright fringe is, so your dark is your B is a dark fringe. Okay, dark fringe at point B. Okay, right? So they want you to find out what is distance AB. So if this one is A, sorry, A is here and B here, from here all the way to here, how many x do you think you have? Remember the distance between adjacent bright fringe is x. So from the first bright fringe to the center, from the central bright fringe to the first bright fringe here, you have one x. From the first bright fringe to the second bright fringe, you have another x. And then from the bright fringe to the dark fringe, you have half of x. So overall, AB is actually 2.5x. That is the understanding here. Okay. Distance from A to B is 2.5x. So from here, you need to find out what is x. Okay. So to find out what is x, since you know that this is a double slit, lambda is ax over d, you want to find out what is x, so it becomes lambda d over a. You know what is the wavelength, which is 546 nanometer. You know what is the distance between the slit and the screen, which is 85 centimeter. You know what is the distance between the slits, which is 0.13 millimeter. Change everything to meter, you will get your x as 3.57 times 10 power minus 3 meter. Okay. So lastly, you know that AB is 2.5x. So just sub in the value and you get your AB as 8.93 times 10 power minus 3. Okay. So far, so good. Right. Then after that, the last question, I just need to explain a little before we can end the lesson. Okay, so let's have a look at the question at the bottom. All right. Now, the laser is now replaced by a laser emitting blue light. State and explain the change in the distance between the maxima observed on the screen. Okay. So they tell you laser is replaced by another laser that emits blue light. State and explain the change in the distance between the maxima. This one, distance between maxima, is actually referring to x. Okay. So what we'll tell you here is that blue light actually has a shorter wavelength. So if you refer to this equation, lambda is equals to ax over d. When lambda decreases, x will decrease. Therefore, the separation is less, no? Okay. That's the answer. This is just one mark, right? They only need to know what happens with some explanation, actually, because they call state and explain. So you have to have those 2 points. Blue light has shorter wavelength, therefore separation is less. The one statement in the middle is something like an explanation to connect both together. Okay. Blue light has shorter wavelength, so according to equation, lambda equals to ax divided by d. When lambda decrease, x decrease. Therefore, your separation will be less. Okay. If you just look at page 9 of your worksheet, I discussed this last week for you guys. Then we were talking about this example that is on double slit interference of light. So the state and explain question at the last part, it was mentioned that the laser is replaced by a laser emitting blue light. State and explain the change in distance between the maxima observed on the screen. What happens to the fringe separation? Simply put, they were asking. So then what I mentioned was this. I mentioned that blue light has a shorter wavelength. And then because lambda is ax over d, you can see that over here, if lambda decrease, x would tend to decrease. Therefore, the separation is going to become less. Okay. Now, how do you know in the first place that blue light has a shorter wavelength? you see, the question didn't really specifically told us what color of light it was. They mainly mentioned to us laser light of wavelength lambda 546 nanometer is incident on the slits. So they only mentioned the wavelength itself, but they never mentioned to us the color. They told us that it was 546 nanometer. So how did I know that blue light is actually having a shorter wavelength? They didn't tell us the color in the first place. If they told us the color, I know that if I refer to this spectrum, Roy G. Beef, given a certain color, and given that I know blue light is over here, I will be able to know whether blue light is actually having a smaller wavelength or larger wavelength. But here the question did not give me the color. So there's the odd thing about this question. They never told us the color. They only told us that they're replacing it with blue light. So the only way you will be able to know that blue light is having a shorter wavelength here is if you know what is the wavelength of blue light in the first place. The wavelength of blue light is around 450 nanometer. It's between 450 to 495 nanometer. So when you compare versus 546 nanometer, this one is clearly less. So to be able to arrive at this conclusion that blue light is having a shorter wavelength, you would have no choice but to know this. Okay, that's the odd thing about this question. It kind of expected you to know the wavelength of blue light, but most of the time in the other questions, it's pretty easy. They will tell you what light they use first, and then after that they tell you what color did it change to. They will tell you the colors before and after the change, so you can determine the wavelength, whether it's an increase or decrease easily. It's just that this one they never told you. Okay, just so you guys realize that. All right. Okay, so let's start the lesson in earnest. Okay, so that part, okay. Now we're just going to go through some other questions that deal with double slits, all right? We haven't been doing much of it, so we're doing more today. Okay, after page 9, can you guys look at page 10? A student sets out an experiment to investigate double slit interference of light, but finds that the interference fringes observed on the screen are too close to each other to be distinguished. What change would help the student to distinguish the fringes? So usually the keyword here is that you just look at what kind of experiment it is. The moment you hear mention of double slit, which is a two-source interference, this equation almost always will be used. Lambda is AX over D. So what they want is that they saw that the interference fringes are too close to each other, meaning to say X is too small. They want you to tell us what change could you do to enable the student to distinguish the fringes, meaning to say they want X to be larger. So based on this equation here, right? Okay. Wait. The new student is joining. Yeah, hi, generally. Can you look at the worksheet page 10? We are under page 10 right now, question 26. All right. Okay, back to what I was saying. If you want to find out what change can you do to help increase your X, this one, lambda is AX over D. X is lambda D over A. X increase if lambda increase, D increase, or A drop. So what you just want to do now is to see which of these changes match with this. So if they ask you to decrease the distance S between the two slits, this one here, this distance between the two slits S is actually your A. Okay, it's actually the A in this equation. So this one, they're actually saying that A is decreasing. This is actually what you want. So this one could be a possible answer. How about the part where they say increase the width of each slit? Okay, increase the width of each slit is more like this. If I were to give you a close-up of the double slit here, a close-up of the double slit looks like this. This one, the center to center distance of the slit is your A. But the slit width is referring to this, how big of a gap the slits are. So when we talk about the width of the slit, it's actually talking about this. Okay, it is not talking about A itself, the distance between the slits. It's actually talking about the width of the slits itself. So you see, this one is talking about something that is not related to this equation. Okay, so this one is not related to the equation. Therefore, no effect on X. All right. Okay, now increasing the width of the slits has no effect on X, but it will have an effect on the interference fringes itself. Okay, the interference fringes that you expect to see on the screen will probably look like this. All right. These are your interference fringes that you expect to see, your pattern of bright and dark fringes. So you changing the width of the slits will not have an effect on the X, on the separation X, but you will have an effect on the appearance of the bright fringe. Okay, because what we'll tell you here is this, bigger width means more light can pass through. More light, so more light can pass through. The bright fringe is brighter. Okay, the bright fringe is brighter. And then dark fringe remains unchanged. Okay, so while increasing the width of the slits does not change the spacing of the fringes, it will have an effect on the brightness of the fringes. It will actually cause your bright fringe to become brighter, because when you have a bigger width, you allow more light to come in, so it's brighter. Okay, the dark fringe itself, on the other hand, does not change because you have complete cancellation. All right, so B is out, nothing to do with fringe separation. Okay, then after that, if you look at D, answer choice C, move the screen closer to the light source. Move the screen closer to the light source. This one, you want to move it closer towards the light source. This one is actually saying that it's indirectly telling you that you want to decrease D. Capital D is the distance between the screen and the slit. So when you move the screen closer to the light source, you're actually indirectly reducing D. So you're reducing D, but here you want D to increase. So this is not what you want. Okay. Then after that, you look at the answer choice D. Use blue filter instead of a red filter. So these are what you call as color filters. All right. If you use blue filter, you're gonna get blue light. If you use red filter, you're gonna get red light. So right now, what you have here is a light source. This one actually emits white light. You're using a red color filter to get red light. So right now, the question says that rather than using red light, you're using blue filter to get blue colored light. Okay, you're using blue filter to get blue colored light. So what you can do here is that you try to compare the relative sizes of your wavelength. So when it comes to color and you want to determine the wavelengths, always remember this. Rho G width going towards the right is where wavelength decreases. Red light is over here. Blue light is over here. So since this is on the right side, the blue light is on the right side of red light, I can say that wavelength of blue light is actually less than wavelength of red light. Okay, so over here, I'll say that wavelength has decreased. So if you want x to increase, you want lambda to increase, but here lambda is decreasing, so this one is also wrong. So our only correct answer is supposed to be A. Okay, C and D is definitely out of the picture. Okay, so this is for this question. Okay, now then after that, if you move on to the same page, next question, they tell you that I'll just clear off the whatever I wrote here. All right, you can refer to the recording later. Okay, now shapes have been damaged by water waves with large amplitudes. These waves could have been formed by adding the displacements of smaller waves. You see, this is the keyword here. They are formed by adding the displacements of smaller waves. Okay. What term will describe this phenomenon where you add the displacement of smaller waves? This one, without thinking so much about it, you should know that it's talking about superposition, because one of the first things you learn under this chapter is that superposition states that where waves meet, the resultant displacement is the sum of the displacement of the individual waves. So it's talking about superposition, not diffraction, not polarization, not refraction. Diffraction, this one refers to spreading of wave through a slit. Polarization is oscillation confined to one plane only. Refraction is bending of wave. Okay. Now, diffraction and polarization is in your AS. You learned this earlier. Refraction is not inside your A-level syllabus. All right. You are not required to really know what is refraction. You learned this under IGCSE or SPM before, but it's not required. You are not required to know this in detail in A-level. Okay. So correct answer is superposition. Okay. So answer for this is D. Okay, then this one is clear. I believe 28, we've also kind of done it before. But I'll just go through this briefly for you. Okay, water waves of wavelength lambda are diffracted as they pass through a gap of width d in a barrier. Which combination of wavelength and gap width will produce the greatest angle of diffraction? Greatest angle of diffraction here, you can just think of it as producing greatest diffraction. Okay. Now, when they say greatest angle of diffraction, the angle is more like this. Let's just say that this is my wave before it hits my slit. And then after it hits my slit, it diffracts, right? It bends. When they say angle, you can think of the angle as referring to this. This is the angle. Okay. Obviously, if you have something like this one is one set of angle, but let's just say the wave bends even more, like this. You notice that your angle is actually larger. All right, so it's referring to how much your wave actually bends. Okay, so in your notes, I wrote some particular equation that allows you to determine whether your diffraction is going to be large. That one is on the page, I think it's in the earlier pages. That one would be on the page 3. Okay, so that time I mentioned to you, if you want to determine whether something is going to have a very large diffraction, you just look at the ratio of the wavelength to width. The larger the ratio, the bigger the diffraction. Okay, take the ratio of the wavelength to the width. So for your case here, this one you can think of it as your width. This one you can think of it as your wavelength. So take the ratio of the wavelength to the width. So lambda divided by W. So from here, what you get is lambda over D. Wait, maybe it's better I just write the working out. This one is 2 lambda divided by half D. So this one you will get 4 lambda over D. I'll just write it separately. Okay, A is 2 lambda over half D. So you're gonna get 4 lambda over D. For B, it is half lambda over half D. So this one you're just gonna get lambda over D. For C, it is 2 lambda over 2D. So you get lambda over D. For D, you're gonna get half lambda over 2D. This one is going to be 1 over 4 lambda over D. So you see which one of this seems to give you the biggest ratio of all? It is only A. Okay, so the answer is A, right? This is the simplest way to evaluate whether you're gonna get the greatest diffraction of all by comparing the ratio of the gap width and the wavelength. Okay, so answer is A. Okay, then that one is okay. Page 11 skip because it's stationary wave. Page 12 also skip because it's also a stationary wave. Then after that, we go through page 13. Okay, page 13. All right. Okay, question 25 is something very similar that we've just done. This one I'll just run through it very quickly. Monochromatic light passes through 2 narrow slits and produces an interference pattern on the screen some distance away. The interference fringes are very close together. What change will increase the distance between the fringes? So notice that this is asking you about how you increase X. They're talking about 2 narrow slits. This is actually talking about double slit. So double slit lambda AX over D. X is lambda D over A. You want X increase, X will only increase if lambda increase, D increase, or A decreases. So you look at all these answer choices, which of them are telling you either one of this? So increase the brightness of the light source. This one has nothing to do with the equation that you have here. So you could say that this one no effect on fringe separation. Okay, but because what I mentioned just now earlier to you, you increase slit width, you cause more light to come in, your bright fringe becomes brighter, right? This one also has a similar effect. You're using a higher brightness of light. So this one in itself may not be the answer. It will not cause a change in the fringe separation, but it does cause something else. This one, bright fringe is brighter, no change to dark fringe. Okay. Now for B, increase the distance between the slits and the screen. This is talking about increasing D. It is what you have here. So this one by right should be the answer, but you can double check with answer C and D. If you increase distance between the 2 slits, this is talking about reducing A. Sorry, this is increase the distance between the 2 slits. Sorry, increase the distance between the 2 slits. This is talking about increasing A, but you want A to decrease here. So this one is out. And then after that, D, increased frequency of light use. How is frequency related to wavelength? You know that frequency is inversely proportional to wavelength. So this means that if frequency increase, wavelength would drop. Okay. So wavelength is dropping here, but you want wavelength to increase. So this is out. So answer is D. Okay. So that one is okay. Right. So this one is all right. Then after that, you move on to 6. The question 26. The following statements describe the diffraction of wave passing through a narrow slit. Which statement is not correct? They want the statement that is not correct. Okay. So wave passing through a narrow slit, you expect it to diffract. Okay. Now, both transverse and longitudinal waves can be diffracted. This is correct. Transverse could be light. Longitudinal wave could be sound. Both can be diffracted. Okay. In the examples that I actually went through with you for two source interference, the double slit itself was already talking about light for one of the examples. That one is transverse wave. And then for sound, sound can also be diffracted. Okay, although the example here didn't show you the sound wave traveling through a slit and then spreading out, sound can also be diffracted. Okay, so for your case here, transverse like light can be diffracted, longitudinal like sound can also be diffracted. Okay, they will spread after passing through a slit. Okay, then after that, you look at the second statement. Diffraction can only be seen with light when the light is monochromatic. This one is actually not true. Okay. What they're trying to say here is that you can only see effects of diffraction with light when the light is monochromatic. Monochromatic here means single wavelength or single color. Okay. So the thing here is that it is not specific to just a single wavelength. I mean, if you try to use white light and pass it through a slit, the 7 different colors in the light will diffract. Okay, it will show you effects of diffraction. All right, so B is supposed to be the answer. This statement is not correct. It's saying that diffraction is only possible with light if it's a single wavelength. But the fact is that it is also possible when you have many different colors, many different wavelengths inside. A case in point is this one here. That time I mentioned to you under the, which part here? Under page 6 or 7. No? Wait, let me see which part of the notes was it. Yeah, it's under page 9 of your notes. I did mention to you before. If you were to use, it's under page 9 of your notes. I did mention to you before, if let's just say you are using, you're talking about double slit experiment, instead of using monochromatic light, instead of using laser light, you use white light. You use white light to pass through the double slit. You will get some sort of interference fringes, but the interference fringes will be rainbow colored. Only the center will be white. Okay, so when you pass white light through a double slit, so if this one is your double slit, and then I tell you you pass white light through, what you understood was that when white light passes through the double slit, slit S1 and slit S2, the light will actually diffract at S1 and actually diffract at S2. So each one of this is actually kind of like a slit in itself. So when white light passes through each of these slits, it does diffract. So it is not wrong, it is not correct to say that diffraction only occurs for monochromatic light. It does occur for white light too. Okay, that's how you get rainbow colored fringes for your double slit experiment when using white light. Okay, so this one is okay. All right, then after that, red light diffracts through a greater angle than blue light. Red light diffracts through a greater angle than blue light. Okay, this one here, you can just think of it as this. This one, wavelength decrease. Red light, blue light. What you do understand was that wavelength of red light is more than wavelength of blue light. Okay, so they're saying right now that red light will tend to diffract at a greater angle than blue light. It will tend to spread out even more than blue light. Okay, so this one, how would you do this? Okay, remember that little ratio of W over lambda? Okay, the one that I did under page 4 for you, under page 3, I think. This one, ratio of lambda over, sorry, lambda over W, my mistake. Okay, the ratio of lambda over W. Okay. That tells you how, that gives you a measure of how much diffraction you will have. So this one, I know that red light is larger in wavelength than blue light. Okay, so if wavelength is bigger, I expect the ratio to be bigger, therefore more diffraction. Okay, this one I'm comparing for red light. Red light is bigger than blue light, so wavelength increase, ratio is increasing, therefore more diffraction. So this one is actually supposed to be correct. Okay, then after that, if you look at the last statement, the angle of diffraction increases when the width of the slit decreases. You again can use this one. The ratio is lambda over W. This one they're saying width of the slit decrease, right? So if width decrease, ratio increase, therefore diffraction increases. So this one is also correct. All right. So D is also correct. So the only one that is actually wrong is B. Okay, select the ones that is wrong. Answer is B. Right, so this one is okay. Then move on to the next question, question 37. Okay, this one requires you to do calculation. You have to use ratio for this one. Okay, now same thing, talking about double slit again. Here they say it's a pair of slits, so you know it's double slit. Okay, so monochromatic light is directed onto a pair of double slits. Interference fringes are 2 mm apart, are observed on the distant screen. Frequency of light used is then doubled and the slit separation is then half. How far apart are the new interference fringes? Okay, so based on what you have here, the moment you see it's talking about double slit, automatically this equation always comes. Lambda is AX over D. So they want you to find out how far apart are the new interference fringes. They want X, the new X. So if I tell you to rearrange this, X is lambda over D divided by A. So now you want to compare the two cases, the first case and the second case. All right. So what you do, what you can see here is that when they made the changes, what remains the same? Here you notice that they say that they changed the frequency, they changed the slit separation. They actually made some changes to F, which in turn means they made some changes to lambda, and they made changes to the slit separation, meaning to say they made changes to A. Okay, so the only thing they did not change was actually D, capital D, the separation between the slits and the screen. So this one, I can say that D is constant, therefore X is proportional to lambda multiplied with D. Sorry, X is proportional to lambda over A. Okay, so from here you can actually split your working into two different types, the short method and the long method. Okay, I just show you the short method first. Now, if I talk to you about this one, frequency of light used is double. What happens to the wavelength? This one, I know that frequency is inversely proportional to wavelength. If frequency is double, increases by 2 times, wavelength would decrease by 2 times. Okay, that is the significance of increasing the frequency. Your wavelength will drop by 2 times. All right, so applying what you've seen there, this one is the first method. If I consider the changes in frequency, I know that wavelength drops by 2 times. So wavelength drop 2 times, that means X will drop 2 times. Okay, this is just talking about effects on lambda. What about effects of A? They told you that slit separation is half. So you consider the effect of A separately now. A reduced, when slit separation is half, that means it's divided by 2. So you say it's decreased by 2 times. A decreased by 2 times, that means X increased by 2 times. So you look at this part here. This one decreased 2 times. This one increased back by 2 times. So the conclusion that you could get is that overall there's no change. Overall there's no change. Therefore, X remains the same. The original value of X was 2 millimeter. So if X remains the same now, it should be 2. Okay, so this one is just looking at it by simple ratio method. If you want to calculate it out, you can. You're supposed to get back the same answer. So this one is the second method that I'll show you, the one that I always tell you is more tedious. Okay, so I know X is inversely proportional to lambda over A. That means X2 over X1 is lambda 2 over A2 divided by lambda 1 over A1, which in turn gives me lambda 2 over lambda 1 A1 over A2. Okay, so now you sum in the values. All right, so if you know that lambda 2 in relation to lambda 1 is actually half. So this one I can say that half lambda 1 lambda over lambda 1 A1 is this, A2 is half of A1, so it's half of A1. Okay, right? So eventually what you see here is that they all cancel off. Lambda will cancel, A1 will cancel, half and half will cancel, giving you just 1. Therefore, X2 equals X1 equals to 2. Okay, no change. So use either one. Method 1, method 2. Method 1 is more straightforward for me. Method 2 is if you are not confident in method 1, but it's more tedious.